Good.
Is that allowed? Am I cheating?
All right, you're
Am I
starting.
cheating if I calculate the contamination, right?
No, exactly. Okay. I should say yes and no. The thing is, for the contamination is like that. If you have some assumption in your about your data, that like how much of them will be actually fraud. If you say that, okay, I believe 5% of my data will be outlier, then you can actually use it, and then the model will use it for just for the sake of label. Remember the function that I showed you, which was a decision function? The actual output is like that. It's just a number. The contamination will help you to map it to 0 or 1. So here, maybe just using, let's say, 0 as a threshold. But if you say, see, I know, I don't know, I know that just 5 sample is negative now, but I know that 10% of my data should be outlier. So it will increase the threshold from, instead of to be 0.0, it will be maybe, I don't know, something higher. Actually, I wanna, so you can use it. That's why I wanna show it here. See, the one that I showed you was a prediction, which is basically with map it to prediction would be 0 or 1, and then that was the score. Here, instead of visualizing that, I would say visualize the destination, the decision function, and just use 0 for now. And it's not working because I'm in a wrong. Okay, I should be here. Here. If I use 0, it will be identical. But if I increase the number to, let's say, 5, see, more sin is anomaly here. And if I even increase it even further, like I'm okay, I have to do that. Okay, everything is anomaly now. More sin, see? So that number means if you know what percentage of your data is anomaly, you can play with it. So it means instead of just using prediction, you can use the decision function. And the only thing that contamination is doing is like saying that, okay, if you know the like 10% of your data is actually outlier, I can shift this value in a way that my prediction will match your assumption. Maybe that's how you will manage to get good number here, because you kind of know the ratio and you use that. So maybe if you just use it randomly, you say, okay, you know what, 5%, or I don't know, 10%, something like that, then you will use it. But if you have no idea about your label, that would be kind of like cheating, because you don't have a label, so you won't be able to match. But if you have a test data, you should be able to use that number and see how is the result on your test data. You see what I'm saying? If you have like a small amount of data, so still you can use it here. But that's the whole thing. Even if you can visualize it, you should be able to do that even manually yourself. You can say, okay, no, it makes sense, or it doesn't make sense, something like that.
Like per se, when you have those graphs of the feature distribution and the two classes, right? What if like the cases for isolation forest that you actually are more like overlapping, like in one of the cases above, would it still work? Probably not, right?
Yeah, exactly. So if they're completely in the same area and you can differentiate, that dimension won't help it. But that's why if you have, that's why if you, let's say here he used, I guess, 93. So overall, if you randomly pick feature in 93, then you will use those dimensions, which is more important, and then you will get that. So because some of the dimension is not like that, for sure some of the dimension won't help you at all if they picked randomly. So that was exercise number 1. I guess we should be able to kinda. So even I tried. I guess I just randomly use 200 max sample. I said max sample is the length of the whole thing, so it means per tree, instead of doing the subsampling, use all of the data instead of doing max sampling, and then contamination. I had some fixed number, which was, I don't know, point something, and then that was the score, which was 0.3, and you got even better number with that. So you see.
Did you use the contamination mode? Because if you didn't,
Yes, I did use contamination, but contamination number for me was something fixed that I defined it somewhere. It was like a small number. So yes, it is helping, but where is my contamination?
Outlier fraction?
Did I use that? Probably. Then I said 15%. So I don't know, maybe it's one variable somewhere. But if you use contamination, it can help. But you can just remove that one as well to see what will be the effect of that. So here, yes, exactly. So it was 15%. If I say remove that line and just let's say put it here, I don't want that. I don't want that. So here I'm not using any contamination score at all, but let's see what will be the result. And it will take a while, and I will run it next. So while it's running, I can switch to the next one, and then we'll get back to it. Okay. So the other algorithm is one-SVM, that you want to see how this model will perform, and then we'll try to do the same exercise for credit card as well, but this time we're going to play with the one-SVM. So one of the difference between one-SVM and isolation forest is like that. As I said, if you want to actually divide these two algorithms to different categories, we can say isolation forest is for unsupervised learning. It means you already have some noise in your data and you want to isolate them. In one-SVM, kind of the assumption is your data is clean. I mean, you do have some space for error that you can have it, and still for that you have to add that kind of contamination score as well. So it means you're saying that, see, I know I have almost like 5% error or noise or outlier in my data. Ignore that amount of data as a like upper hand, and then like for like as an upper bound of I don't know the number of anomalies that you can have in your data. So you can kind of help this one-SVM to fit the data, but the idea here is the data is clean, and the only thing that you kind of trying to do is, let's say, fit a boundary around your data. So you want to learn the distribution by making a boundary around the data.
So in your training data, you are going to remove the minority cases completely to train one-SVM, right?
Kinda. I will talk about that, but I just want to get back to that one. See here, I didn't use any contamination score, and actually my F1 score is 0.33. So not bad, even though actually it's better because my contamination score was 15%, which was wrong. When I removed that, I got even better number. So the thing that here I used was, as I said, you can say what is the max sample. As I said, it will generate a subsample of a data, and then it will try to make some cut. So then you can define how many samples you should choose. Here I said, use all of them. Instead of doing subsampling, for each tree, actually use the whole data and try to cut it in different places. And then I managed to get good number here. So it was not about so sometimes maybe it is about features, but here it was mostly about the number of samples in your tree. So that was the hyperparameter that was actually helping me here. So it was not just contamination, it was mainly about the feature. But for different data set, it might be different. So you can try for MNIST or for KDDCOP, it might be not that one which is helpful. So that's why we should always try different hyperparameter to see which one is actually helping us in that data set.
Well, I'm confused though, because it's like a clustering method, right? Unsupervised, right?
Yes.
So then how is it becoming a predictive model now? Because every time that you build so in this case you're using the whole data as the training data,
yes.
right? And then what is the one that you're how do you get all these predictive measures?
See, for those synthetic one, I can't compute anything because I have no idea which one is actually outlier. Is it this one outlier or not? Usually I can say yes, but I don't have any label. That's why I picked this data set which was credit card fraud, or even for MNIST that you can create it, that you can use it. The idea is like this data set is labeled. But for training the model, I'm not looking at any label. I'm just saying that these are lots of credit card transactions that I'm looking at it. I'm trying to use one model, which was isolation first. I want to label them. And then I want to see how it's performing. Then I'm looking at the label to just compute the score. So label here is just for us to be able to see how the model is working, but usually in real life, you don't have access to it. Good? Okay. So, one-SVM. Here, I'm trying to use one-SVM to be able to make a boundary around that data. Here, even I can do, okay. The feed prediction will give me 0 and 1 as well, or I can do the score sampling, I get the actual number. It will be similar to that decision function, but that will be like a kind of like a distance to that boundary. Then I can use that one as well. So for now, I just want to look at the prediction, which is 0 or 1. And then you can see one-SVM can kind of find the boundary on my data, and if the boundary is not there, I didn't visualize that one, but if you want to see, it will be something maybe around that part of the data set. And then based on that, it will say if anything is on the other side, is outlier for me. So the whole thing about one-SVM is in generative model, like a GMM or all those models, try to learn the distribution. Here, instead of learning what is the data, you're trying to say, how can I, make a boundary that most of the data will end up being inside of it.
So then, do you remove the contamination cases in training the model or not?
Yes. See here, for one-SVM, you should actually have no outlier in your data set. But the thing is, because usually you have it, you can kind of switch it to be, you can kind of convert it to unsupervised one by having that NU, which is like a kind of like a contamination score as well. It means you have some assumption about your data, and you can kind of test it. Here you can have a number. Here my number, as you can see, is 0.15, which is like a 15%, and that would be like an upper bound. I'm just saying that make a boundary around my data, but I'm giving you the permission of be able to ignore to the most 15% of the data. So that's the thing that it might not do that. It might just say 5%. 5% was enough for me to be able to make that boundary. But you're just making that, like, you're just giving him a permission, giving the model the permission to be able to ignore 15% of the data for the sake of being able to make that boundary around your data. So that's the definition of contamination score or layer fraction or whatever you can call it here, which will try to help they want SVM to be able to handle unsupervised data that you still have noise in it. So then they call it in SVM, if you're actually using SVM for classification, they call it like hard margin or hard boundary or soft one. And the soft one is you're letting the model to have some noise in it and to be able to escape some of the sample to be able to have maybe a better boundary or I don't know, hyperlane in your data to be able to split to two class. So sometimes you have lots of noise in your data, or I don't know, if you're doing classification, sometimes some of those sample will be in the other side. So then if one-SVM or even a regular SVM won't be able to kind of find any boundary. So that's what we're saying. I know that data is not completely normal, so I'm letting you to skip some of the samples in your data set, and that's is the upper bound of it. So if I change it, then you will see that then it might actually make it harder for the model to kind of make the boundary.
Yeah, when I was going through this slides, I was wondering if does the anomalous data, does that go into the model as well, or are you just using the true data and you're trying to fit the boundary?
Here, as you can see, all of them are in the model. So that's what I'm saying. If I make that number to be 0,
yeah,
I'm letting the model know that, see, I know my data is clean. You have to make a boundary which will cover every single thing in my data set. But something we're saying that, okay, I know my data that might have some noise, so don't do it.
Don't take everything.
Yeah,
like,
so
try to find
you're kind of like relaxing the model to be able to letting the model to be able to skip some of the samples.
So is this kind of like a regularization kind of thing, like where you try to make sure your boundary doesn't get too complicated?
Yes, you can see like that. Yes, exactly. So it means like you're saying that for the classification, it will be like that. That's why they have like an epsilon there that will say that then they're kind of the soft merging. They're saying that, okay, you can skip some of the samples to be able to make maybe a smoother or better line, right, instead of try to come up with this, I don't know.
Very weird.
Yeah, something like that. The problem is one-SVM won't be able, like SVM won't be able to do that because we want to actually make one line, like a hyperlane, but it will make things harder for the kernel, so you have to find a more complicated kernel to be able to do the same thing that you might be able to do that with just linear. So, any question here? So here is still the again the prediction. You can just use the prediction, or you can use the score, which I want to do that as well. And if you change the score, you might be able to get different number. We can increase it and then getting different number in it. So, any question? Everyone, okay. Good. So everyone knows how SVM works. Then that would be the second exercise, which means we have to do the same thing for, I guess it should be in the other one. This is number 2. Here, as you can see, if you actually use all of the data, it will take lots of time. one-SVM is not as fast as isolation first. And maybe that's one of the drawbacks of it, because SVM basically has, if the number of dimension as well is higher, it will make it slower for the SVM to be able to find the best hyperlane. And that's why, to make it a bit easier for the model, I kind of decrease the number of samples you have for the sake of time. But after the I don't know the workshop, you can actually, or after the session, you can actually use the whole data to see what will be the score for all of it. But then you have to just wait, maybe I don't know.
Can you try one-SVM on the tool thing?
Oh yes, of course. Let me. Use the prediction itself. There you go.
Oh, so it's not as good as the
Maybe because it was maybe harder for the model to be able to find the boundary, but I would say it's doing pretty good. But this one is skipping all these nodes here. But for sure, yes. If you have a better, more dense data set, it will be a lot easier for the model to be able to find the boundary around it. And as exercise, you can report that one.